Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to take up the 7th numerical on waveform coding techniques. Let me read out the question first. The data from 10 different sources are brought to a processing center over wires and are sampled, quantized, binary coded and time division multiplexed. The multiplexed data are then transmitted to the monitoring station. The bandwidth of each signal is 100 Hz. The maximum acceptable error in the sampling amplitudes is 25% of the peak signal amplitude. The sampling rate must be at least twice the Nyquist rate. Determine the minimum cable bandwidth needed to transmit these data. Right, let me start with the solution now. Let us first write down the given values. We are told the bandwidth of each signal is 100 Hz. We know that the bandwidth of the signal also represents the maximum value of the frequency component of the corresponding signal. So, this as per the low pass sampling theorem is represented by W, which is equal to the highest frequency component of the signal. We are told that the sampling rate must be at least twice the Nyquist rate. So, let us start by finding the Nyquist rate for each signal first. This is equal to 2 multiplied by W. Therefore, it is equals to 200 Hz. Since the sampling rate is given as at least twice the Nyquist rate, the sampling rate Fs is now given by 2 times the Nyquist rate, which is 200. Therefore, the sampling rate is 400 Hz. Please note this is the sampling rate for each signal. I'll just modify this previous part as sampling rate for each signal. We know that the sampling rate is also expressed in terms of samples per second. So, 400 Hz is equal to 400 samples per second. Since we are told the total number of signals are 10, the total number of samples for the 10 signals would then be, this is equal to number of signals, which is 10, multiplied by number of samples per second for each signal, which is 400. So, this is equal to 4000 samples per second. Coming back, let us now read this particular sentence where the maximum acceptable error in the sample amplitudes is 25% of the peak signal amplitude. So, I'll start with the equation for the quantization error. For the given system, the quantization error should be less than or equal to 25% of, that is 0.25 multiplied by 25% of the maximum signal amplitude. So, I will call it as X maximum, where X represents one of the input signals, divided by the bandwidth of each signal, which is 100. So, this is equal to X max divided by 400. In this equation, the quantization error is unknown, so is the value of X max. So, we can't find anything here. I will now write the equation for peak signal quantization error, and this is given by delta divided by 2. This is applicable for both the mid-riser as well as the mid-thread quantizer. We know that delta, which is the step size, is given by 2 into X max divided by L, where L represents the total number of quantization levels. Therefore, the peak signal quantization error is equal to, I'll substitute for delta, which is 2 into X max divided by L. Then we have a 2 in the denominator here, therefore it will be multiplied by 1 by 2. This simplifies to X max divided by L. Let me call the quantization error here as equation 1 and the latest one as equation 2. So we will now compare equations 1 and 2 and try to find the value for L. So it will be x max divided by 400 equal to x max divided by L. The x max get cancelled in the LHS and RHS. So what remains is L equal to 400. Now L here, as I said previously, is the number of quantization levels and is given by the formula L equals 2 power n. Therefore, now 400 should be less than or equal to 2 power n, where n represents the number of bits per sample. By using the simple logic of the power of 2, I find the value of n is equal to 9. How? 2 to the power of 1 is 2, 2 to the power of 5 is 32, 2 to the power of 8 is 216 and 2 to the power of 9 is 512. So, the value of n equal to 9 here satisfies this condition, and that is why I will be choosing the value of n as 9. Right. Once we have found the value of n, we can now come back to the numerical to find the value of the minimum cable bandwidth required. To find the minimum cable bandwidth, I will first find the minimum bit rate. Let me start with that part. We know that the minimum bit rate of the set of signals given is equal to number of bits per sample multiplied by the total number of samples. Therefore, the minimum bit rate will be number of bits per sample is 9 multiplied by total number of samples we have found previously is equal to 4000 samples per second. Therefore, this is equal to 4000. This is equal to 36,000 bits per second. After finding the minimum bit rate, it is very easy to find the cable bandwidth because the minimum cable bandwidth is simply equal to the minimum bit rate divided by 2. Therefore, the minimum cable bandwidth is equal to minimum bit rate divided by 2. That is 36,000 divided by 2 equals to 18,000 Hertz. This is the answer for this numerical. Right. That is about this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.